Thank you very much, everyone, for coming. This is the second time I've delivered this. It's a brand new talk. And it's a talk of two halves. So the first half is about security technologies built into modern web browsers and how I built a really big problem with the sheer quantity of data that we work with. And the second half of the talk is how I solve that problem. So the problem came from one of my projects. So I started this as a side project, just a little bit of fun. I started building it in around 2013-14, and it ingests telemetry from web browsers. So Report URI is the service, and built into all modern web browsers now, you can ask for the browser to send you telemetry back to a nominated location. You could send it to yourself, to your own domain, or we operate the service on your behalf. And this could be telemetry about security events or security-related events. This can be about performance, about availability. There's all of these native mechanisms built into the browser, and you can turn them on and say, when something happens, please send the telemetry data here. And that is what we do. We ingest this data, we make graphs and dashboards and things. Now, one of the most common things that people use us for is to mitigate a quite nasty attack called cross-site scripting. So we heard Jim in the keynote this morning talk about cross-site scripting. I was in Philip's talk in here earlier, also talking about cross-site scripting. And of course, the number one protection that Philip talked about, output sanitization, right? We should be taking care of cross-site scripting by properly encoding all of our outputs. But in security, we should practice something called defense in depth, which is having more than one protection for a given problem. If our primary line of defense fails us, we have a second line of defense that can save us. Now, a cross-site scripting attack might look something like this, right? It's a very simplified example, but somebody finds a way to inject a script tag into your application. Now, if I look at this, right, the domain evil.com, probably don't want this. The file name, this is going to do not good things when it gets into the page because I have this extra context, right? The browser doesn't have that. The browser looks at this, and if it makes it into the page, it's yep, that's syntactically valid. I'm going to pull in this asset, I'm going to execute the JavaScript, and now all of the things that you type into the website are probably going to be Ajaxed off somewhere in the background, and it's going to steal your username, your password, credit card data, whatever you type into the page will be gone. Now, cross-site scripting, again, as we saw with both Jim and Philip's talk, has been an increasingly common problem over the years. And original kind of attacks might have been defacements. We can do funny things if we get JavaScript into your application, but then cyber criminals come along, and they don't want to do funny things. They don't want to, just deface your application or do something annoying. They want to make money. Right? Cyber criminals, just your garden variety thief, but in the cyber world, online, they just want to make money, just the same. This is what motivates them. And we've seen a selection of fairly prominent groups and kind of collectives over the years. Now, fortunately, CoinHive no longer operates, but CoinHive was a group, a collective of people no one really knows because these people often don't get caught. But what they would do is they would abuse this kind of genuine product. So CoinHive was proposed as a genuine thing. And what they would say is you've got your website, you want to monetize your traffic. People put paid advertisements on their website, right? And they're really bad for performance. There's all of the valid privacy concerns around loading third-party advertisements and tracking and things like this. So CoinHive built this product, and they were like, hey, what you could do, when you come to my website, I'm just going to run this little piece of JavaScript in the background. And what it's going to do is it's just going to mine a little bit of cryptocurrency, Monero. Right, so you go to my website, you load the page, my JavaScript goes into your browser, and whilst you're reading my blog post, news article, whatever, I'm just borrowing some of your CPU, right? And you're going to pay me a few cents in Monero. Then I don't have to subject you to adverts and tracking and privacy invasive performance things. And it was, this was the idea. Now, what the attackers realized was, well, hey, if we just grab this library and I can stick it in all of your websites, then all of your visitors will be mining the Monero but sending it to me. And this became known as cryptojacking, right? It's if I can get my JavaScript into enough people's websites and those websites have enough visitors, I can just watch the Monero roll in. Now, cryptojacking kind of came as a trend, and it was like very, very popular, like especially like 2015 to 18 kind of time, and then just fell off because they weren't making so much money, right? Like you can't make so much money mining Monero with a CPU, which is terrible, in JavaScript. So it was like, okay, this works, but if you've got the ability to inject arbitrary JavaScript into someone's application and you want to make money, you're going to look for like, what thing can I do that makes the most money? And cryptojacking was great, but it didn't make enough money, and it quickly fell out of favor. And we saw something else fill the gap. And this was a still ongoing threat to this day. And again, we don't really know who these people are. We refer to them as MageCart. And what they do, when they find the ability to somehow get that hostile JavaScript into your application, they just have a tiny little keylogger. And there's a couple of different variants that the different groups use, but they all work in basically the same way. They go onto the page, and they're either looking at key press events and Ajaxing them out the back, or they look for a form submission, and when they do, they grab all the text elements on the page and Ajax the whole set out the back. Now, the other thing that it has is a little basic regex, and they always run a regex against the URL for the current page. And as long as they can find a substring match for cart, checkout, payment, something like that, they're like, oh, our JavaScript's running on a payment page. What types of information do people type into payment pages? Name, address, 16-digit card number, 3-digit security code, expiry date. So now, instead of making their $2 a day with their Monero, they're like, hey, if we can grab credit card details off a payment form, and what they do, they sit on it for like 1 week, 2 weeks, nobody's noticed them, they keep collecting them, because the payment form still works, right? Like I go to the e-commerce site, I buy the thing comes in the post. They just took a silent copy of my card data. And once they go for as long as they can without being noticed, they're like, okay, we've got like 50,000 credit cards right now, let's hit them all with $100. You take 50,000 credit cards, charge them $100, big money, right? We're not talking a couple of dollars a day in Monero, we're talking real hard cash. Now, this is all falls under the category of cross-site scripting. We've got some hostile JavaScript in our application that shouldn't be there. And if we're talking about traditional, like reflected or like what Philip showed before, persistent cross-site scripting, output encoding is the way to solve that. But sometimes people get screwed by their third-party dependencies, right? If your third-party dependency suddenly gets some like extra bits of JavaScript at the bottom that are a keylogger, they're still going to load, because it's not come in through your application, it's come in through a dependency. So we have this second line of defense that we can use to try and protect ourselves. Now, content security policy, CSP, is a hugely powerful mechanism. And one of the most dangerous attacks that you can neutralize with CSP is cross-site scripting. So if you ever hear about someone talking about CSP, and I do this too, they're usually always talking about cross-site scripting because it's the most dangerous thing that you can neutralize. So CSP kind of became known as like the anti-cross-site scripting defense mechanism, but it does so much more, right? If you look at it and think cross-site scripting, that's like one of 10 things it can do for you. So if you do ever look at it, go deeper, there's more it can do. But the idea of content security policy is you have this basic HTTP response header, right? So just like your normal response headers that you've got in your application, you can see we just add a new HTTP response header called content security policy. And as you can kind of guess by the name, this is going to be a security policy around the content on our site. So what CSP allows you to do is control what should my page do, right? Like where do I load assets from? Where do I send data to? Like what's supposed to happen? And then when something happens that isn't supposed to, the browser can be like, oh, hey, like according to the security policy, like this shouldn't be happening. So the most powerful type of content that people like to control with CSP is JavaScript, because it's the most dangerous type of content that we load. So if you look at how we control JavaScript with content security policy, CSP has a wide selection of directives that we can use to kind of assert our control over that particular type of content. So we have the script source directive here. So I define the header and I say script source. And what I'm telling the browser is like, where should I be loading JavaScript from? Now, self means match the current origin of the page. So if I'm on my personal site, like scotthelme.co.uk, it means you can also load JavaScript from that origin. And then I'm also, let's say I pull jQuery from the jQuery CDN. Now, if the browser loads the page and we come across the script tag that we just looked at earlier that said evil.com, the browser's going to be like, going through, pausing the page, and it's like, right, we got a script tag source attribute evil.com. It's not there. It's not going to load. So that script tag will get thrown out the window. It's not supposed to happen, so it won't happen. Now, this is a hugely powerful protection. When you tell the browser, this is what should happen on my site, as soon as something outside of what should happen actually happens, the browser will just stop it. And like I say, it's not just about loading JavaScript. You can control everything on the page with CSP. So we've got the default source here. I generally say, like, it's, as my default position, I can load stuff from myself, right? You should trust yourself. If you don't, there are things that I can't help you with. And then we take a look at things like the script source, right? So where am I going to load JavaScript from? We've got the style source, style sheets, image source for images. So things like child source is like iframes. So this is a really powerful control. For us at Report URI, we do payment card processing for subscriptions. So on our payment page, there's only one iframe we should load, and it's our actual payment iframe from Stripe. So if you go look at our payment page, we are like, there should only be one iframe here, and it's stripe.com. And if it's someone else, something has gone really badly wrong. But content security policy, again, is looked at, and people think, oh, well, we can control like where stuff loads from. But it's not just where stuff loads from. You can also control where can stuff go. So we have things, there are other directives like connect source. So if that little piece of JavaScript somehow gets onto my page and it's trying to AJAX that data out the back, or you've also got form action, maybe they build a form and try and submit it with a post to some third-party location, the browser will check against this and say, okay, well, this JavaScript is running on the page, it got here somehow, but this page is only allowed to send data to this location or that location. So if this JavaScript suddenly starts trying to skim your visitor's credit card data, it can read it, it can access it, it can grab it, and then it goes to fire the post, and CSP is like, no, that's not supposed to happen. It's not supposed to go there. So this is such a powerful mechanism. It can be a little bit tricky. Like the biggest problem with CSP usually is listing all of your third-party dependencies, because most of the times I speak to people, I'm like, hey, where do you load JavaScript from? And they're like, well, I don't know, look at all the script tags. Because there's no controls over this so far. So you define the policy. You send this policy to the browser. And let's say you get hit with MageCart, right? So you've somehow ended up with a piece of JavaScript on your site that's not supposed to be there. Your user goes to the payment page, they type in their card number, and something in this policy is going to stop it. Either the script source is going to catch the script coming in, the hostile script, or something like connect source is going to stop the data going out. So in the case of MageCart, we've just prevented like a pretty serious data breach. Some of the big companies that have been hit by MageCart recently, Ticketmaster, British Airways are the most notable ones for me in the UK. Just the British regulator has fined Ticketmaster for losing all of people's names and addresses and credit card data, millions of pounds. The American regulators are also fining them. Then the payment card industry, who's like Visa and MasterCard, because they have to reissue all of those customers' cards, that's really expensive. So then Visa come along and they're like, hey, we had to reissue all of these cards, and that costs like $500,000, so you're going to pay for this. All right, so just because they had like 2 lines of JavaScript on their payment page, they're getting like millions and millions and millions of dollars in fines and things coming in. And it could have all been stopped with a single HTTP response header. Now, the good thing about having the CSP in place is that it will stop the attack. But if I'm sat here on my website, I presume I don't know I have hostile JavaScript on the payment page, right? But the page has gone to your browser, and your browser has just taken defensive measures. It stopped the attack. But I don't know that, do I? Right? Because that's just happening like your browser and your browser and your browser. What I need is for you to tell me that happened. And this is where the reporting mechanism in content security policy comes in. Because one of the last directives that you should look at is the Report URI directive. This is where I shamelessly stole the name of the service from because I'm terrible at naming things. So we just call the service Report URI because that's what the thing in CSP is called. So what you do with the Report URI is you specify a URL where you want the browser to send information when something goes wrong. So as you can see here, you register with us, you get a vanity subdomain, and what you're saying is, look, when there is a problem, when you have to take some kind of defensive measure, I want you to send the information here so that somebody actually knows that that's just happened. Now we call this violation reporting in CSP. And what the browser does is it fires a HTTP post out of the back when the violation happens, and the HTTP post goes to the reporting point. Now, the post has a JSON payload. We've got a bit of a snippet from the top of one here, and you can kind of see, exactly what's happening here, right? As I said, there's loads of different types of telemetry like this the browser can send. So this one says, hey, this is a piece of telemetry. It's a CSP report, right? There's loads of other things. You can check them out later. Right now, we're looking at CSP. So here's a CSP report. I was on this page, and something on the page violated the script source directive. And the browser will also give you a copy of the original policy to say, look, this is what I was working with, and this is what happened. And then the final thing is, what did I block? Like, what's on the page that shouldn't be there? In this case, it's the script tag that we were looking at earlier that we definitely don't want. So now, just like before, this piece of JavaScript was still blocked in the browser, right? Like, the attack didn't happen. We've neutralized the attack. But I still need to know about it, or in this case, Jacob still needs to know about it, because they need to go fix the actual problem, right? The JavaScript got there somehow. They need to remove it and close the hole where they got the JavaScript in. So to me, and I realize I'm massively biased as the operator of a reporting service, reporting is essential. Because if you have the policy and the browser is blocking stuff and you never find out, it will just stay there, right? And I'm like, we're kind of missing some of the solution here. So to me, when you have reporting, I send the policy, the hostile JavaScript is blocked, the report comes back to me, and then I remove the JavaScript. That's the solution as I kind of see it, right? Yes, the CSP has protected you, and I've not had that terrible data breach, but I still need to go fix the original problem. And with reporting, I can find out about it, and I can go straight to the point and be like, right, this page, this script, how did it get there? Let's remove it. So this is what we do. And over the years, Report URI, us as a service, we've become more and more popular. Now, I built this because, God, it's like 2013 or 14 or something. When I first looked at this capability in the browser, I was like, wow, that's really cool. I want that for my website. And I was like, going to Google, CSP reporting services. I spent like 5 minutes on Google and I couldn't find one. If you spend 5 minutes on Google and you can't find it, it doesn't exist, right? So I was like, okay, I'll build one. So I literally just built one. I was like, I can't find one, I'll build it. So I built it and I was like, actually, this is really cool. I'm getting some awesome data, like the telemetry from all of the other mechanisms as well is amazing. I was like, I'll stick like a pretty website on it and I'll just open it up and be like, hey, everybody, like I built this thing. Thinking like me and, Niall and 2 other people would use it. And we did in the first month, right? It was basically like me, Niall and Troy. So in our first month of like actually operating the service, we only processed 1 million reports, right? So in the whole month, all of our users sent us in total 1 million of those JSON payloads. But then people started to learn about CSP and all of these other mechanisms. And they're like, hey, this cross-site scripting thing is bad, right? Cryptojacking is really not good. MageCart is really not good. And everybody gets hit with like cryptojacking or MageCart. And then there's the news headlines and all of the news articles are like, oh, well, if they've been using CSP, like they would have been okay. So the interest in CSP starts to rise. And as time goes by, we start to get more reports because when people enable CSP, they want reporting as well. So 2016, I looked at our data to get all of this. We're doing 1 million reports in a day. It's like, okay, million post requests. It's not like 1 million get requests from cache. It's like a post payload. We've got to do stuff. There's database activity. But 1 million a day is still not so bad. Time keeps going by, right? 2018, we're now doing that in an hour. So we get 1 million JSON payloads an hour coming in. I'm like, okay, you're still within like my view of the realms of that being reasonable. But then things like MageCart really take off, and the adoption of CSP is now really taking off because of attacks like MageCart. Organizations get hit with like $20 million worth of fines, and they're like, CSP, like, we don't want that anymore. So we get to 2021, and I was like, how long does it take us to process 1 million reports on average? Now, I generated these numbers in December for NDC Oslo, and it took us, on an average, over a 24-hour period, because we have like major peaks and troughs when countries are awake and asleep. Over that 24-hour period, I averaged it out, and I was like, on average, like how long does it take us to do 1 million reports? 15.4 seconds. We can do 1 million JSON payloads on average in 15.4 seconds. And then this morning, when I was preparing, like final preparation for this talk, I was like, I'll just update this slide. I'll just go get some more data. Like, how long does it take us to do 1 million JSON payloads now? And we can do that on average over the last 24 hours from like 10 a.m. this morning to yesterday, it will take us 11.2 seconds to receive 1 million HTTP post requests with a big JSON payload that we have to do something with. Now, throughout this whole process, like I built this thing for like me and 2 of my friends, and it was terrible, right? Because it didn't need to be good. And every time we've hit one of these like major milestones, I've had to do some significant re-architecting of things because I was like, I never expected it to get this large. It was never meant to do this much stuff. And eventually, handling the volume became a really big problem because, like I say, these are post requests with JSON payloads. Like we have to do stuff with them. There's database activity. If these were GET requests from cache, like I could just hook this up and my laptop could take care of this. But post requests with JSON payloads is a really big thing for just me, right? So over time, we've done various different things to try and make this process more efficient. Things like normalizing the JSON payloads. So what we realized was like every browser and even different versions of the same browser have like slight nuances with how they will construct the JSON. So we're like, right, we're going to normalize these down and flatten them as much as possible to kind of like deduplicate them on the way in. We use Azure Table Storage as our backend. So we now store the reports and we use the partition key as like a 1-hour time bucket. Because what we found in our UI, you could go like really granular on the search and be like, show me this page from like 14 minutes past and 16. Most people just search by like the hour or the day. So we were like, we'll drop the granularity and you can only query by an hour as the maximum resolution. But it meant that we had significantly less work to do on the back end. Deduping similar reports. So this was like looking into the actual fields because some browsers, for example, if you have like query string parameters on the URL, some browsers will send them and some won't. So it makes the reports look different, even though potentially they're the same. So we did some basic deduplication, trimmed a few things up. Spammy reports, this is a really big one. If you have a browser extension that changes like the font on the page for readability reasons or something like that, if it injects a font into the page, and the content security policy doesn't allow fonts from that location, it's like, whoa, violation of the content security policy. There's a font happening here that shouldn't happen. So we look for those kinds of things in our inbound telemetry, and we try and identify like these false positives, these spam reports as we call them. And we're like, hey, look, you know, if the user's got a browser extension in their browser, there's nothing I can do about that. And I also don't need to know about it. So we just take those and we throw them away, right? We don't even let them touch the back end. It's like, just get rid of as much stuff as we can because we've got too much stuff coming in. Now, the final thing here was we originally had unlimited data retention, right? Because again, it was like me and 2 other people using it and it was fine. And now we're getting like, you know, millions and millions of reports in every couple of minutes. I was like, we need to have sensible data retention because we only have 90-day data retention. And I checked this morning, we've got 3.9 terabytes of JSON on disk, right? And we only have 90-day retention. So we were like, yep, 90-day retention, chop the tail off. And you know, we can hopefully keep the amount of data we have as small as possible. Now, in particular, this 90-day retention one will come back to haunt me in a minute because it makes particular things really tough to do. Because one of the biggest things that we want to know with content security policy, when we have a report coming in, the number one thing that people ask us is this: have we seen this before? Like, if you've got a problem on your page and you get 1,000 visitors to the page, all 1,000 of them will tell you. And I'm like, I only need one of you to tell me, okay? Like, once I know and I've been told that I have seen this before, all of the rest of them, we can just like scoop them together and we don't need to know. So have we seen this report before? So Jacob's running the NDC security site, and this report comes in. And he wants to know from us as a service, like, hey, have we, you know, is this new or have we seen this before? So what do we need to do as a service? Well, we need to go back over all of Jacob's data and try and see if we can find, like, have we seen this report before? So first of all, we've got vast quantities of data. We took it down to the 90-day retention to try and make that amount of data smaller. But then the problem is we can't really answer the question. The question that we can answer now is like, have we seen this report before in the last 90 days? Because we've time capped it now. So we don't know if you've seen this before ever. We only know, like, have we seen this before within the last 90 days for which we have data? But that's still a huge quantity of data to search over to look for a single JSON payload. So we decided to solve this with something called Bloom filters, which is what the kind of like the second half of the talk is about. because we want to be able to answer this question. We don't want to answer this question with the last 90 days caveat. We want to answer this question, have we seen this before? And we want to answer this question fast, because as soon as this report hits our edge, we want to know then, have we ever seen this before? We don't want to know, later or tomorrow. We want to know now. But running these queries in real time, when we're getting tens of thousands of reports a second, doing those tens of thousands of queries against the back end was just not going to happen. So I set out to kind of investigate the options, and I arrived at something called a Bloom filter. So first of all, we're going to explain the basic structure. This is a very small Bloom filter. In production, you would make all of these numbers a lot larger. But a Bloom filter is basically just an array. So you can see here we have an array of bits, and all of the bits are set to 0, and there are 10 of them. So the width of the array is 10. Now, when an item comes in, what you can do is you can say, we've seen this item, and we will add the item into the filter. So then, when we query the filter later, we'll know whether or not the item was in there. So to insert an item into the filter and say, we've got this piece of data and we want to mark it as having been present, we have to insert 2 bits into the array, 2 hash functions. So k equals 2 means when we insert this element into the array, we're going to set the bits at 2 locations using 2 different hash functions. Now again, in production, we're using like 8 on our main filter. These numbers are much smaller for simplicity. So if k equals 2, we have 2 hash functions, and the hash functions are going to give us the index in the array to set the bit at. So we've got h1 and h2. If you had, k was a larger number, you'd have all the way up to hk hash functions. So we've got 2 hash functions. The really important thing about these hash functions is they have to be pairwise independent hash functions. And I'll show you what that means on the next slide here. So we have our Bloom filter. It's just an array of bits, all set to 0. We've had a new report come in, item A. Could be any item. It's a CSP report for us. And we want to mark the presence and say, we've seen this report. We want to mark its presence in the Bloom filter. We want to add it to the filter. So we take our hash function, our first hash function, h1. We hash item A, the inbound JSON payload. And then we modulus it with the width of the array to give us the index where we should set the bit. So in this case, we come up with index 2, and then of course we've got 2 hash functions, so we get the second hash function do exactly the same thing. We hash the JSON payload, mod it with the width to make sure it gives us an index inbounds, and it's number 4. So now we know the 2 locations that we need to set a bit in the array. So we set them. There's the first one, and there's the second one. This means that this piece of data, item A, this CSP report, is now marked as having been seen and been observed, right? So the next one comes in. Let's add one more item to the filter. We've got item B. So this is the next CSP report that comes in. We want to add this to the filter, exactly the same process, right? We take the first hash function, we hash the new report, mod it with the width, it gives us the index of 6. We take the second hash function, mod it with the width, it gives us the index at 9. So we're going to set those 2 bits as well. So now we've added 2 CSP reports to the filter, and the filter looks like this. We've got the 2 indices set for the first report and the 2 set for the second. So let's say the next report comes in. The next report is item C, and we want to say, have we seen this before? This is how we ask the question of the filter. So this is the next report that comes in. What we need to do is we need to hash it with the first hash algorithm. So we've got hash it with h1, mod it with the width, look up index 4. Is the bit set? Yes. Right, but then we've still got the second hash function. So we hash it with hash function 2, mod it with the width, check the bit at location 7. Is it set? No. If we had seen this report before, this second bit would be set. So now we can say we have not seen this report before, because if we had, the bits would be set. So now we can say for sure, we have never seen this thing before, right? 100% confidence. We have not seen it before. But then let's say we get the next report, right? And it's a duplicate. It's item A again, right? We've just had the same thing reported to us. We go through the process. We take the first hash function. Obviously, we come back to number 2, right? The second index. And then we take the second hash function, same as before, right? Because it's exactly the same report. And it says look up the bit at location 4. Now, both of these bits come back as a 1. Because we've seen item A before, and obviously when we saw them last time, we set the bits. So now we can say, we've seen this item before. Or can we? Let's take a look at the next report that comes in. right? Another new one. We've never seen this before. It's item D. I've not talked about it. It's another new report that's just come in. Let's see if we've seen this particular report, right? Take the first hash function, hash the item, mod it, index number 4. Take the second hash function, hash it, mod it with the width, index number 9. Both of those bits are set. Now, the first bit from H1 is set when we set item A earlier, and the second one, index 9, was set from item B. And we've had what we call a collision. So we've now tried to look up item D, and the Bloom filter is going to tell us that we've seen this thing before, but we've not seen this thing before. It looks like we've seen it because the two bits were set by collisions with other items in the filter. Now, Bloom filters, to use their proper name, are what we call a probabilistic data structure. And what that means is, with a Bloom filter, you can ask it a question. Is this item in the original data set? Have we seen this thing before? And the Bloom filter can only give you two answers. Now, the answer that we want and get a lot of the time is definitely no. If one of those bits is not set, you have never seen that item before, because if you had, the bit would be set. But when we get collisions, and this is where the probabilistic part comes in, if the filter says yes, it's saying, yes, we've seen this before, with a certain probability that this could be a false positive. Because collisions can set the necessary bits to make it look like an item is present, even though the item was not present. So the answer can only be definitely no, or maybe yes. But we can control the probability of false positive. This is one of the things that we can control with the construction of the filter itself. So if we take a look at setting up the filter, there are a few different things that fall under our control. So we've got W, which was the width of the array, right? My array was only 10 bits wide. If I made that array a lot wider, those first two items and then item D would probably not collide. As you make the array wider, you reduce the chance of collisions. You need to know, within reason, how many items you plan to put in the filter. Because if you think about it, as you add more and more items, the chance of collision goes up, so you need to make the filter wider to compensate for that. If you imagine a Bloom filter where all of the bits were set, so if I took my 10-item filter a minute ago, once all of those bits say 1, the Bloom filter is just going to say yes to everything, right? So if you overpopulate Bloom filters, they're completely useless. So you need to have a rough idea of like how many things are we going to put into this filter, like how much data do we want to represent. With these numbers, you can then determine how many hash functions do we need. How many bits should we set per item? So this is determined, this is not generally chosen. And then the other thing that you can have an impact on is that probability of false positive. If the Bloom filter says, yes, you have seen this before, what are the chances that that's a false positive? And if you take that probability and you want to drive that down, you can, but it will impact the other variables. So if we take a look at the current filter that I'm trialing right now, then we have chosen a couple of these values, but we've chosen the width of the array and the number of items that you can put in, and you can derive the others from that. So if you have the width, then you can just set that as a value. But if you don't have the width, you calculate that from the other values that you have chosen. So there are Bloom filter calculators online. Just ignore all this stuff, right? You can choose, like we did, so we know n, the number of items we're going to put in the filter, and I know what my desired false positive rate is. So I also declare p. And from n and p, you can see, you can then calculate w and k. And it kind of makes sense, right? If you know you're going to put n items in this filter, and you want a certain chance of false positive, that's going to drive up the width of the array, right? Because you need more space to avoid those collisions. So as you tweak these values, you can control the two that you want to control, for us, n and p, and then it will dictate what the other two need to be in order to hit those objectives. There's loads of calculators online. Don't try and figure this out. You don't need to. So if you want to calculate the width of the array, I was like, okay, how many items are we going to put in this filter? Now, I know how many reports we've processed over time. We just keep a running counter. And I'm like, okay, but how many of them were like duplicates? How many of them were duplicates, but they looked kind of similar, but the JSON was slightly different? And, we didn't know the number, and I still don't know the number. So I was like, okay, I'm just going to take a guess, like 7 billion reports. So this is distinct reports. I know we're doing millions and millions a minute now, But remember, like by the time we normalize them and deduplicate them, we're talking about 7 billion distinct JSON payloads. I was like, I think this should be enough, right? Like, hopefully this will be enough. I still don't know, right? Now, I also know what I want my probability of false positive to be. I've got a reasonably low tolerance to this. I don't want to be getting false positives all the time. So I set my probabilities between 0 and 1. I go for 0.01. I only want a 1 in 100 chance of a false positive probability. So from having n and having p, we can now calculate the width. How wide does the filter need to be? How many bits do I need in order to achieve the false positive probability? And it will also tell me k. So when we calculate w and roll this out, it comes to 8.4 gig of RAM. Now, in the first instance, I was like, holy crap, that's a lot. But then I was like, well, actually, like how big is the data set that this is representing, right? If we've got 7 billion JSON payloads, and you know, like some of these things are pretty big, right? And we can have this filter in memory with only 8.4 gig. Like the data set on disk is terabytes and terabytes and terabytes. We can keep this filter in memory. Okay, like we spun up a separate Redis server for this, right? And it's so easy to get a Redis server with like 16 gigabytes of RAM these days, right? And it's so cheap. I was like, okay, actually, my initial shock, it's kind of okay, right? We're looking at like $100 a month for a Redis server that can handle this. So I was like, okay, this is reasonable. And the only thing left then to kind of calculate is K. So we now know what the width is because we've calculated the width. We know the number of items going in the filter. We can now calculate K because those are the only two requirements. So we just run the math out and it says you need 7 hash functions. So for every CSP report that comes in, we have 7 hash functions that set 7 bits in the array, in the Bloom filter. And this is it. So now this is what we are currently trialing at Report URI. This is what we're currently using for our inbound reports. We're not using this as a definitive answer yet because this is still like very much experimental. I don't know if 7 billion is going to hold. Maybe it will be way too much and I could have gone smaller. Maybe at some point we'll use up 7 billion items in the filter. But right now we're actually using this as the first indicator because that definitely no is a really useful answer. If that report comes in and the Bloom filter says, you have definitely never seen this before, we can jump to action straight away because we know we've never seen it before. 7 hash functions takes like a fraction of a second. We're querying against a Redis cache in memory. We don't have to go touch the back end with like the terabytes of data. This is so fast and so efficient. And we use it as our first marker. When it comes back and says probably yes, you've probably seen this before. Right now, we still do the check because like we go to check the back end because we're trialing this. Now, for us, this makes sense because the definitely no is the thing that we're looking for. If it says you've definitely never seen this before, there's no questions. This makes probabilistic data structures like this, makes them suitable for certain tasks and not suitable for others. So I thought I'd give some other real-world examples rather than kind of like my specific use case on where we see Bloom filters used successfully, and maybe they will kind of resonate with some of you. So the first one was with a company called Akamai. So they're a large cloud like content delivery network CDN provider, and they use Bloom filters to avoid something called a one-hit wonder. Now, when you're a really large CDN provider, you reverse proxy your customers, your caching assets for them, right? So my page goes through the CDN loads the page from the origin and puts it in the cache. And then the idea is like if people keep going to view the page, then the assets are in cache. So they want to keep as much stuff as they want, like as they can in cache, but they don't want to keep unnecessary things in cache. And a one-hit wonder is a phrase that's used to refer to something that is requested once and never requested again. So if you've got one-hit wonders in cache, like somebody requested the asset once, you put it in the cache and then it just stays there forever and nobody ever asks for it again. It's a complete waste having it in the cache. So they use a Bloom filter, right? When the request comes in, they say, has anyone requested this before? And if the Bloom filter says no, it means it's the first time this asset has ever been requested. So they fetch it from the origin and they serve it, but they don't cache it because nobody's ever asked for it. And then they set the item in the filter. The second time somebody asks for that same asset, they say to the filter, have we seen this before? And the filter says yes. with probability of false positive. So then they're like, okay, we'll get it, we'll cache it, and we'll serve it. So you're only ever caching it the second time the asset gets requested. And then that eliminates all one-hit wonders. And I'm going from memory on the white paper, but I'm pretty sure they eliminated like 70% of the items in their cache by removing one-hit wonders with the Bloom filter. So this is a really good implementation. Now, another really good implementation that I've seen, is safe browsing, right? So Google safe browsing is the ability for someone to like report or flag a website as being harmful. It's got like malware, it's got some phishing on there, whatever it is, like some bad thing. And then they will put it into the safe browsing data set, and then your browser won't allow you to go to that page, right? We've all seen probably something like this. So you try to go to the site, and the browser's like, whoa, there's malware on the page. This is a known phishing website, whatever. You should not go there. Now they do this with a Bloom filter. You imagine the size of the Google Safe Browsing data set, right? They've probably got a list of like billions of pages, of URLs. Your browser isn't downloading this like honking big file with all of the domains in. It downloads a tiny little Bloom filter. And every time you go to a page, every time you visit a URL, it checks it against the Bloom filter and says, is this in there? Now, if the Bloom filter says, no, this URL is not in there, you can go to the website because it's not in the safe browsing block list. Now, we get to the yes. Yes, it's in there, but there's a probability of false positive, right? Google don't want to be like, oh, hey, you can't go to this website because it's filled with malware, and it was a false positive, and actually your website is fine. So there's a separate API call on the back end. So then it will actually directly query the Google Safe Browsing API and say, is this URL on the block list? But you only have to do that query if the filter says yes. Every single time the filter says no, I mean, we don't see these very often, right? So like 99.9% of the time, the filter's like, no, it's not on the list, no, it's not on the list. And I can just keep browsing, and there's no queries reaching out to like the Safe Browsing API. But the one time when you go to it, and the filter's like, yeah, you know, like this is on the list, then it will query out. So you're preventing those queries like the vast majority of the time. No, because the Bloom filter is really small. Chrome uses lots of RAM on your machine for other reasons. The Bloom filter is tiny because you can represent significant quantities of data with a tiny Bloom filter. Now, this sounds like immediately when I say this, sometimes people are like, wait, Google's sending the URL to like their own API? This sounds like tracking. So first of all, the Bloom filter prevents the no answer. You don't need to do the query. When you do the yes answer with probability of a false positive, it uses something called k-anonymity to query the Google API. So just to let you all know, it's not actually sending the full URL off to Google and tracking you. That's a really good question. So the question was, if you have a filter, and let me know if I misinterpret this. If you have a Bloom filter and we end up overpopulating it, can you like somehow recover and like increase the size and fix it? The answer is no. Once you've defined the width of the array, you cannot later change it because it shifts the index of every item in the array. So this is like kind of a thing I address at the end, but it's a really good question, so I'll address it now. You have to know the two things that you set, like so for us, we've got the number of items and the probability that we control. The number of items has to be reasonably accurate. There's a pretty good error tolerance in there, right? And you can overpopulate it slightly. But if you go to if we have 7 billion items in our original plan and go to 14, the filter's going to be trash. So you cannot recover later if the dimensions are wrong. And this is why right now it's kind of like a secondary piece of information for us to query the filter. But the definite no is still useful. Overpopulating the filter only affects the probability of false positive. So like if you're getting the definite no, it's still a definite no, and that's the thing we need anyway. Now another kind of like useful example of a Bloom filter, have I read this article before? Right? You ever log into a news website and you go there and it's like, hey, you should read this article next. The website wants to know, have you read that article before? So they have a per user Bloom filter, and when they take the URL of the article, and when you visit it, they insert the URL into the Bloom filter. And then when you next load the homepage, and they're like, hey, these are the top 3 most common articles today, they check against the Bloom filter to see if you've already been there. And if you have, they just drop it and go to the next one and say, oh, you should read these 3. So this is implemented on Medium. This is really cool. This is how they do their recommendations of something that you should read without recommending something you've already read. They use a tiny little bloom filter per user. Now, the kind of final example is something that I've implemented. So I'm sure everybody's very familiar with Have I Been Pwned, run by Troy Hunt. He also has the Pwned Passwords API. So the idea with the Pwned Passwords API is that if a user is registering on your service, you can take the password that they're trying to register with, and you can query it against this API and say, like, has this password been observed in data breaches before? Like, is this a common password? Is this a terrible password that's been previously observed? Now, the Have I Been Pwned API uses the same k-anonymity model that I just talked about, so you're not actually sending the password. You can look that up offline. It is a safe API query, but it's still an API query. Right? Every time a user registers or logs in, you want to check the password. Has this password been seen in a data breach somewhere? So it's outbound calls. You got to go hit the API. We've got network activity, availability, perhaps. The other thing that you can do is you can download the data set. You can download the whole corpus of all previously observed passwords in data breaches. And it's like 18 gig. And I'm like, okay, that's pretty big. Can we take 18 gig and can we make it like more acceptable with a bloom filter? So I downloaded the whole data set, I crunched the numbers, and because I know that there are only like 712 million passwords, I can smash the numbers accurately, right? So I can build the filter, the data set doesn't change. And now we have a couple of gig filter in memory, and when you give us a password to try and register, we check it against the Pwned Passwords data and say, have we seen this password before? Now the false positive rate when we do this is 1 in 100 million. Right, so we only get, if we have 100 million users register, please, we will only tell one of them that their password has been previously seen by accident and prevent them from using it. Now in that scenario, you can then fall back to the API and say, well, the bloom filter said we'd probably seen this, now we'll do an API query. So for those 100 million registrations, if there's only the one person using it, we would only query the API once. So this saves like a huge amount of expense, having an external dependency, network activity, availability, everything else. So there's loads of cool things that you can do with bloom filters. And bloom filters act as the base data structure for several other data structures as well. Bloom filters are not the only thing that we're now using. I kind of like fell into the rabbit hole of probabilistic data structures, and now we have them everywhere. So, you look at a bloom filter tells you one thing. Have we seen this before? Yes or no? Yes, with false positive probability, which we now know. So it's yes or no. But maybe you want to know, like, how many times have we seen this before? Right, okay, cool. We have counting bloom filters for that. Right, slightly different structure to what I showed you, but very similar. It allows the counting of items. Same probabilistic nature. And what the filter can tell you is the item is greater or equal to the threshold that you set, or it's definitely under. So basically, like, how far off do I want the count to be? Right, so then it's like, oh, well, okay, counting bloom filter is great. What if I put something in the filter and I want to like unset that? In a bloom filter, you can't do that because you're potentially unsetting the bits for other items as well. So for that, you have to use a cuckoo filter. Cuckoo filters allow deletion of items from the set, right? And you can keep going with this. We're also using this, a count min sketch. Now, a sketch is just a two-dimensional bloom filter. The bloom filter I showed you earlier, one-dimensional, right? Sketch, two-dimensional. That's the only difference. It allows frequency analysis on events at high volume. And of course, we're processing like thousands and thousands of payloads a second. Frequency analysis is really helpful for us. Now, count min sketches can overcount, but they can never undercount. So if you query the sketch and say, like, what is the frequency of this report? It can tell you that you've seen it a few more times than you have, but it will never tell you that you've seen it less than you have. So we use this. You can define the tolerance for overcounting and the probability of false positives and things like this. But the final one, and the one that we use right now, like the most frequently, is something called top K. So top K, again, is built on a sketch. So it's just a two-dimensional bloom filter. It runs a binary min heap alongside the sketch. So you can keep track of the most popular items, like the top K, the top most popular items. So we have like our top K is top 10. So it keeps track of the 10 most popular items that you've seen by volume. So we take all of our inbound reports and we run them through top K on the way in. And the top K keeps track of the 10 most frequent reports in the data stream. So we can look at this at any point, and we can say, like, right now, like, what is the top most frequent report that they're always CSP, because it's our most voluminous report. So it's like, for us, it's like, what is the most popular CSP report right now, right? Because if someone is at the top of the chart, we'll take a look at that, reach out to the customer and be like, hey, you're sending us loads of these reports. Like, have you got some major issue, maybe a misconfiguration? Like, what's going on? But we can do frequency analysis on, at peak, we're doing like 80, 90,000 JSON payloads a second. Right, this top K is like 4 megabytes in Redis. That's literally all the data structure takes. And the final one, which I'm currently looking at, is a hyperlog log, which is basically like how many, so I'm trying to use a hyperlog log to answer the question from earlier, which is how many distinct reports do we see? Hyperlog logs will count distinct items in a stream. So you take all of the inbound report data, you pipe it through the hyperlog log, and it will tell you how many distinct items has it seen in that stream so far. So if we can figure out over a reasonable period of time how many distinct reports we can see, I'm hoping we can extrapolate that forwards and come up with an accurate number. But these are all so fast, and like the hyperlog log again, megabytes, tiny little data structure, super, super fast to do it. The processing overhead of top K and hyperlog log on the way in for us is like nothing. I don't care, right? It's so insignificant. When you look at how valuable the data is, it doesn't matter. So I fell down the rabbit hole of probabilistic data structures. Hopefully there's something in here that you see and you're kind of like, oh, maybe we could use it for this thing, or maybe it would be useful for that. I acknowledge fully, like, they're not perfect, and sometimes, especially with like the false positive probability on Bloom filters, that makes them not acceptable for a lot of use cases. But sometimes, like all the examples I showed you, you can work around those limitations, and they can be good enough to save you a seriously large amount of work. So I want to wrap it up there, because like last time I did this, I got so many questions, we ran out of time. I want to make sure these last 10 minutes are good enough for us to ask questions. So if you want to punch in a question and like you don't want to ask it, I'll put the Slido link back up for you. I'm going to open Slido now. I'll take them from the audience, and I'll take them from in here. That was such a fast question hand. I'm worried. Go on.
No, this is a very simple question. What is the most common route by which your customers are getting the bad JavaScript coming into the content that they serve?
Okay, so what is the most common route that our customers are ending up with cross-site scripting?
Yeah.
So, like the most common one at the minute is being screwed by your third-party dependencies, right? By a very, very long shot. Right now, we're really not seeing people like, hey, someone found like a cross-site scripting flaw like direct in our application. And I have to caveat that, because if a group like MageCart, and they've been really active recently, if they go after a popular dependency, they might compromise like 1,000 sites, right? But then if they go after one application directly and find cross-site scripting in your app, they get your site. So I don't think it's that the cross-site scripting vulnerabilities aren't there. I think it's just the attackers are going for like the more efficient ways of winning. So that's just the current trend that I see.
And how are they managing to compromise the third-party?
So one of the most notable examples was when the ICO, which is our Information Commissioner's Office in the UK, they're our data privacy watchdog. They're the government organization that fine you for data breaches. They were running CoinHive cryptojacking on their site, because it's like data breach from the data breach organization. They find themselves, I'm not kidding, right? They find themselves. So they had, as a government organization, they have like a really high requirement for accessibility, and they were using a provider for like a text-to-speech plugin. And the provider had their JavaScript in an S3 bucket with reused credentials. The attackers got in, changed the script in the bucket, straight into the government site. And that was like 4,500 sites that we found, because they compromised the common dependency. So yeah, like it's just such an easy way for them to win with the volume of sites. A lot of the time, the vendor won't tell us how they got screwed, right? We just know that they did. Any more in the audience? Yeah, back there. So do you mean like the script itself that they're using, or like the location it's loaded from? Yeah, so, and I'll reiterate the question again for the audience. Let me know if I got this wrong. But basically, like if we're observing, like a new location that hostile JavaScript is suddenly coming from, is there like a, some kind of like feed of information that people can use? So threat intelligence like that is really expensive because it's really hard to get. So we have our own internal threat intelligence feeds that we use for exactly that. If we've got, we currently monitor like 47,000 sites. And if like 1,000 of them suddenly get a new JavaScript dependency, I'm like, well, either they all just deployed that at the same time, or maybe like a common third-party dependency has been compromised and we're seeing something like MageCart. We're currently looking at like what to do with that threat intelligence feed because data like that is like mega, mega valuable. And I'm like, what do we do with it? And like, how do we do it? I don't know. And we only kind of started seeing this recently by accident and also because of the volume that we have, right? We can only spot trends like that at volume. So right now, this is super new for me, for us. There's only 4 of us. So we're kind of trying to answer that question. I don't know is the current answer. Yeah, I mean, like, and there's plenty of like platforms and things that will take this. We want to see what we can do. One of the questions here on the Slido was what kind of hash functions? So it really depends. We're using rebloom or Redis Bloom, which is like a fully supported Redis module for Bloom filters and all the other data structures, and they use Murmur. So that's what we currently use. I don't know what other implementations use. You'd have to check on, if you're going to build your own, or we just use one of the Redis modules to do this for us. Any more questions in the crowd? I'm fully aware we're like minutes away from free beer, which is like the biggest thing that's ever happened to me in Norway. I went out and had 2 beers last night, and then I ran out of money. Go ahead. For the big report filter, yes.
Yeah. Then you said that Google is using it for Chrome.
Yes.
And then you said it was no memory at all.
Yeah, it's tiny. Because they've only got, so the question, sorry, I'll repeat the question for the audience. We're using like an 8 gig filter in Report URI, and then I said the filter in Chrome was really, really small. So first of all, the safe browsing data set is curated. So once websites are no longer hostile, they get chopped off the list. So they're keeping it just to like the current set of malicious URLs. And also like that list is only in the millions and tens of millions, and it's just a URL. We have like 7 billion JSON payloads. So when you it's a totally different kind of data set. They're working in the millions, we're working in the billions. So when you kind of curate it and make it that small, the filter obviously goes down in size a lot. And yeah.
Yeah, I mean, in the counting part, if you can count the occurrences of this report, can you also map those counts, for instance, to the source or to some other information in the reports, or it's just count over the entire volume?
So the question was, if we're doing the count, can we like link the count of that particular report back to the origin of it? So if I just go back to like this slide here, I can potentially answer this in the time I have left. So the short answer to your question is yes and no. So the problem, so very, very, very quick and oversimplified introduction to a counting filter. Instead of just setting the bit, you put the count there. Every time you reset the item in the filter, you just increment the count. And then if we're setting 7 different counts, collisions will artificially increase the counts, and that's why the count min sketch is called the count min sketch. You pull the 7 counts and you look at the lowest one because collisions have artificially increased the others. With a Bloom filter, with a hyperlog log, with count min sketch, you never get the original data back. You have to have the report come in order to query the filter. You can never get the data back out. But for us, the CSP report gives us all of the information at the point that we query it. So we can look at like, where did it come from, which of our customers based on their domain and things like that. So like, yes, you can, but only because you always have the data when you're doing the query, not from the filter itself. So that's why it's no. Yeah.
You said your filter was 8 gigabytes.
8.4, I think.
That's per customer, right?
No.
But don't you need one Bloom filter per customer?
So yeah, so really good question. The question there was, I said my filter was 8.4 gigabytes, and the question was, is that per customer? And the answer was no, because basically when the report comes in, we just want to know, like, have we seen this individual report before globally? right? And generally speaking, like no customer sends us the same report because all of their URLs are different in the domain anyway. So right now, if we can say we've never seen this before, we 100% need to take action on that report. And then we'll do a database query and see which customer and things like that. So we don't do like any currently per customer filters. We have global service filters. So yeah, like it's just one 8.4 gig filter for everything. Things like the medium example I showed you, they have like tiny per user per customer filters, but we don't. All right, we got like 30 seconds. Are there any questions? No, I'm going to be at the party. Once I've had 2 beers, we can talk more about balloon filters. So thank you very much for coming, everybody, and have a great night tonight.